In Chapter 12, one of the big things is to be able to recognize what reagents can do what in reactions. So number 8 is asking us to identify these said reagents for each of the transformations. And you can start anywhere in the wheel. If you want to start with the top here, we have an alkane, and we need to add a bromine group to the most substituted position. There's no functional groups in that beginning alkane, so we can add Br2 plus light to give us bromine at the most substituted position. From that alkyl halide, we need to make here in the center a disubstituted alkene, and it is the least substituted one that could possibly form on that structure. So I will use 2-butoxide, which is my bulky base, which is the same as that. So that's going to remove this beta proton and eliminate that bromine. Next, we need to add an alcohol to the more substituted position. So here you can use H2O with acid. Because it's going to the more substituted, I don't really have to worry about a rearrangement there. So I can use H2O and acid. Otherwise, you could also use the Hg with water, followed by sodium borohydride. If you want to put an alcohol on the less substituted position, that's when we need to use the borohydride. Or the borane here. In the next reaction around the clock here, we have 2 bromines getting added to the alkene carbons. So we use Br2. If you want to add a bromine with a hydroxy group, this is Br2 plus water. For a dihydroxylation, there's a couple of different options here. This stereochemistry is not specified, so you could use OSO4. Other options for this one is to use a peroxy acid, followed by water. And that's going to give you the alcohols anti to each other, whereas the OSO4 will give it syn. Otherwise, you can also use KMNO4 and sodium hydroxide. To place a bromine at the less substituted or the anti-Markovnikov position, you want to use HBr plus peroxide. And then if you want to go from the alkene to the alkane, this is H2 platinum. So those are all the reagents that you would need for this particular problem. Here we're dealing with alkynes, so I'll just start at the top again. We'll just call that one A. I'm having a ketone formed from an alkyne, so we use acid, water, and the mercuric acid. To make the aldehyde, we want to use 9-BBN. For 2 bromines added in an anti-fashion to each other, and the alkene stays put, this is just going to be 1 equivalent of Br2. And if you add an excess of Br, we'll add 4 bromines. In the next one, we're cleaving that there under oxidative conditions. This is ozonolysis plus water. In this reaction, we're adding a carbon right there. So NaNH3 and CH3Br. If I want to go from the dihalide to the alkyne, I use excess NaNH2. To go from alkyne to this Br2 here on the more substituted, this is HBr excess. And then you can do an elimination of that also to get the alkyne, so that's excess NaNH2 again. To go from alkyne to 1Br, this is 1 equivalent of HBr. And then if you have 1Br there, we can add more HBr to get to the dibromo compound there. All right, reagents here, these are reduction reactions, so you want to remember what each of the reducing reagents do. If we have an alkyne, we want to make the trans alkene. This is where we use NaNH3 with liquid ammonia. That goes through a radical reaction, and that's the most stable radical that would form is the trans. If I want to reduce it all the way, I use H2 platinum. And if you want to stop it with the Z alkene, this is H2 with Lindlar's catalyst. All right, here we're looking to propose a synthesis. In this reaction, I am noticing that I've added one carbon. This part of my molecule is the same as this part. There's one way right now that I know how to make a carboxylic acid, and that is from an alkyne. So if I had this alkyne here, I can make the carboxylic acid. And if I look at the alkyne in terms of my starting material, that's that same starting things here with acetylene. So I can start with acetylene, add this group to it, and then proceed with my reaction. So I'm going to go ahead and do that. So acetylene, sodium amide, I'm going to add this beginning starting material. So this is going to attack here and kick that off. So this is the compound that is formed. This is the new bond that was formed there. And then once I have this, I can do ozonolysis followed by H2O. That would give me the carboxylic acid. I would lose one carbon and the other one would go to form carbon dioxide. So C is going to be kind of a similar process. You can see that isopropyl group hanging off on the end there. The one way that I know how to make an alkyne is to go through, one way that I know how to make an aldehyde is to go through the alkyne. But this one maintains all of the carbons. If I notice here, there's only one carbon that's getting added overall. And if I go through this alkyne here, that's going to keep the two carbons. We're not going to lose any there. But if I go through this carbonyl, if I go through this carbonyl and do an ozonolysis, then I'll end up with that aldehyde. So that's what I'll do there. So I'll start with this alkyne. And to get to the alkyne, from the alkyne to the alkene, I can use H2 Lindlar. And then do ozonolysis, DMS. To get this product and also formaldehyde. Here we're looking to propose some more syntheses. And again, I'm going to observe that this carbon is probably this one. Again, we're adding one carbon here, just that one. So we're probably going to do another ozonolysis. So the reaction process is the same. We're just dealing with a different functional group set here. So if I was doing my retro, I'd have this plus that. So I need to get to that Br there. So to put a Br on the end, I need HBr plus peroxide. Once I have that, in a different reaction here, I'm going to use NaNH2, followed by that compound I just made. And then I can do the ozonolysis. All right, in letter E, it's a similar process here. I need to add a functional group because this has none, and this has 6 carbons. So I have the right number of carbons. I can imagine if I was doing an ozonolysis here, these are connected together. So where 1 and 5 are bonded, there'd be a double bond there in order to do that. So I can see that this can come from my starting material right there. So I'm going to add my functional group. I want to do an elimination with a small base to give me the Morse substituted alkene. And then do ozonolysis to cleave the oxygens. And that is the gist of the chapter 12 reactions.